All right. Last class, we began our conversation on chemical kinetics, aka the speed of a reaction. Just to quickly recap what we covered, the theory behind chemical kinetics. Number one, chemical kinetics surrounds the theory of collision theory. Collision theory is a model that explains the rate of a reaction on a molecular level. As a model, it does have a few requirements. It states that for collision to occur, well, for a reaction to occur, the molecules must collide, the molecules must have sufficient energy, and the molecules must be in the correct orientation. But the actual frequency and rate of the collision depends on the temperature, the concentration, and the size of the molecules. That then led to a conversation about rates of a reaction, where we define rate as a change in concentration divided by a change in time. Don't forget, change in concentration is just a change in molarity, and a change in time, well, that can be in seconds, minutes, hours, or days. What we traditionally expect in a chemical reaction is, as the reaction progresses from the very, very beginning, that the reactants are high in concentration, and by the time the reaction is over, it decreases. Similarly, at the very beginning of a reaction, we expect there to be very little product, such that by the end, there's pretty much only product. This very simple graph tells us one important detail. It says that the reactants we expect to decrease, that is, they will have a negative slope, and products overall increase, having it a positive slope. In the question we did, we simply asked, over 6 hours, hydrogen peroxide decreased from 1 molar to 0.5 molar. Just asked us to calculate the rate of decomposition, where, of course, the rate is simply equal to the change in concentration divided by the change in time. When we plugged in our values, we, of course, got a negative value overall. The negative is not a red flag. In fact, it reflects the direction. The fact that the reactant decreases and leads to a negative rate overall is in line with expectations. So just as we saw in thermodynamics, the negative sign, or sometimes the positive sign, reflects the direction of the quantity we're referring to. We then looked a little bit more detail into the factors affecting rates of reaction. We talked a little bit more detail about things like surface area. This is why we crush medication. It's why we would sometimes dissolve a pain tablet in water, fast the relief. We talked a little bit about temperature. We talked about how, generally speaking, a 10-degree increase doubles the rate. That's why we refrigerate food, to slow down the expiration process. Then we ended our discussion of factors with talking about catalysts. Just a brief reminder, catalyst is a substance that increases the rate of a reaction without being consumed. It does so by providing an alternate, aka a shorter pathway, one that's easier to overcome. That then led into a more technical discussion about rate laws and their expressions. We said for a generic reaction here, A plus B gives us DE. The rate of the reaction is equal to some constant K multiplied by the concentrations of the reactants raised to some powers X and Y. We, of course, know the square brackets refer to concentration, and K is our new term, our rate constant, a rate constant that depends on the reaction. X and Y are also new concepts. In this case, these X and Y labels are known as the order of the reaction with respect to each reactant. They are not necessarily equal to the stoichiometric coefficients. If they are, that just happens to be a coincidence based on the question at hand. You can only determine the order of the reaction using real data. Real data means I would have to provide you with a table or some sort of context to say, here's a reaction. We, of course, did an example like that where we looked at a specific reaction, and I provided you with a data table. I provided you with, over the course of many trials, the concentration changes, and so does the rate. We were able to go over a few questions that simply asked us to provide the rate law. Now, I'm not going to go over this part because we're going to do another question today. But the next thing we're going to talk about under kinetics is what's known as integrated rate laws. So we've talked a little bit about how we expect the concentration of a reactant or product to change over the course of a reaction. And of course, we expect that to either be a positive slope overall or a negative slope. Said that in the wrong order. Of course, a downward slope is the negative, and the upward slope is the positive. When we introduce graphing to any sort of analysis, we introduce a concept of extrapolation. In other words, if we know what the point is here, then could we reverse engineer to figure out what the point is here? May sound pretty roundabout, but really what I'm trying to get you to remember, maybe way back in algebra, is the equation of the line y equals mx plus c. Where, of course, y and x represent our x and y axes. M is our gradient, and c is our y-intercept. For anyone familiar with the equation of the line, you know in principle just how powerful it can be. It's used, of course, to predict information about a data set. You can plug in y, calculate x. You can plug in x, calculate y. And as long as you have some sort of graph to accompany it, you know or can calculate the gradient, and you can know or calculate the y-intercept. So this very basic premise becomes very important within chemical kinetics because we know there are various types of orders. Zeroth order its graph is what we would expect. X-axis is time. Y-axis is concentration. And the slope is overall negative. If we generically label the chemical A, then we can actually adapt that y equal mx plus c equation. What do I mean by that? Well, in this case, we know specifically what our x and our y-axis is. We've already given them labels, so we can actually incorporate them. We can say that our y-axis is A, concentration of A. Our gradient is K, the rate constant. The x-axis is time added to the y-intercept, which is technically also the concentration of A. To distinguish these two concentrations, we give them the label AT and A naught. That's a 0. And of course, as we can see from the graph, the gradient is overall negative, so that is a negative KT. This is the integrated rate law for zeroth order reactions. its rate constant is our what we classically expect molarity per second. But a very interesting concept that arises when we talk about the speed of a reaction is the half-life. The half-life can be described as the time taken for a substance to decrease by half of its amount. So for example, if we had, let's say, a sample that weighed 120 grams, if its half-life is, for example, 6 hours, then every 6 hours, it goes down by half. Half-life is the amount of time taken for a substance to decrease by half its amount. This is what's most commonly used in radioactive dating. Scientists are able to calculate the amount of a specific substance that exists on a person or object, and knowing its half-life, they can age it or determine the age of it. So of course, since we know that reactants decrease, the half-life becomes a very interesting concept to understand, because it's good for us to know, well, how long does it take for the reactant to decrease to half? Deriving half-life of 0th order. Half-life has the symbol T subscript half, because it is the time taken to get to half of its original amount. We're going to start with our integrated rate law. We know that is concentration of A is equal to negative KT added to concentration of A naught. We can say that at the half-life points, the concentration of AT is equal to half A naught. Where does that logic come from? Well, if we consider A naught, or that naught, as initial, and that T as final, then the final amount of A is going to be half the amount of the initial. That's half-life. It's the amount of time for a substance to decrease to half of its amount. So if the initial amount is 10 grams, then the final would be 5 grams, because every half-life it goes down by half. So we simply say that it is equal to half A naught. We can then plug this into our equation. We can say that this is equal to A naught over 2 is equal to negative KT plus A naught. We can rearrange this equation to say KT is equal to A naught minus a naught over 2. Take a second to understand for yourself how I got to this point. I've rearranged the equation. What I've done is I've carried over the negative kt, and I've carried over the positive a naught over 2. That explains where they came from and why their symbols are what they are, aka once you carry over the negative kt, it becomes positive. Once you carry over the a naught over 2, it becomes negative. Now, don't let the labels scare you. Remember, you know what this is saying. You can read this. It's saying the initial concentration of A minus half of it. Let's try to put it another way. X minus half X. Does anyone want to take a guess what that final answer would be? It's half X, right? 1 minus half is half. Therefore, kt is equal to a naught, over 2. To get t, we are going to divide both sides by k. This tells us t half is equal to the concentration of A all over 2k. Where, of course, this entire time, we've been working under the assumption we're trying to do half-life, so that T can be very specifically labeled T half, as in T half-life. This gives us a very simple formula to calculate the half-life of a substance. All we need to know is how much does it initially have, its initial concentration. And then we need to know the rate constant of the reaction, which, of course, as you see from Tuesday's class, that's something that can be determined experimentally. What we just did was called a derivation of half-life. We made an assumption about some value. We were specifically looking at half-life. We made a mathematical assumption, plugged that assumption in, and got a simplified equation. You do not need to know how to derive, but it's important to understand where this came from. As a formula, it will be provided to you as part of the reference sheet, so you don't need to memorize it either. But we went through the derivation, so you know and understand where does this come from. It's because we plugged in our assumption. That's for 0th order. Next up, 1st order. In the case of 1st order graphs, its x-axis is still time. That's in common. However, its y-axis is the natural log of the concentration. That is ln. If you have your calculators, please grab it out. Look for the ln function on your calculator. It's traditionally near the log function. Maybe the second shift of that button or right beside it. We're looking for the ln function. It's normally near the log function or the 10x function. It's this ln. In the case of a first order reaction, with its y-axis being ln, its slope is again negative, such that we're able to say that its integrated rate law is simply ln of AT is equal to negative KT added to ln of A naught. Where did this come from? All we did was try to adapt our y equal mx plus c equation. We know our y-axis. It is ln of A. That means we also know our c-intercept. We know our x-axis is time, and we can see that our gradient is a negative slope, hence negative k. In the case of first order, the units of k is 1 over a second. And its half-life is 0.693 divided by k. Where did I get the t half-life from? Well, just as we did over here, I simply plugged in the numbers, the assumption, and got a final expression. Let's prove it to ourselves. Remember, the big assumption of half-life is that the final concentration of A is equal to the initial divided by 2. This is the big assumption that we make. If we plug this into our equation, we get ln of A naught divided by 2 equal to negative KT plus ln of A naught. Rearranging just as we did the previous one, this leads us to KT is equal to ln A minus A naught over 2. Whoops, KT half. This is equal to ln 2 upon dividing both sides by k. We get that the half-life is equal to ln 2 over k. And if we plug ln 2 into our calculator, that is where the 0.693 comes from. Just as before, though, you do not need to know this derivation. You just need to understand where this equation comes from. What's up? Oh, sorry. Thank you for catching. That's just a typo. Thanks. So just as before, you do not need to know how to do this derivation, meaning I'm not going to ask you on an exam, derive it. But you will be asked questions where you'll be using the half-life or calculating the half-life. It's important you understand where that equation comes from. Next up is second order. In the case of a second order graph, as they all do, the x-axis is time. The y-axis, on the other hand, is 1 over a naught. This time it's a fraction. And this slope is actually positive overall. We can adapt the equation of the line to say that our integrated rate law is simply 1 over AT is equal to KT added to 1 over A naught. Please notice I've been trying to make my T as in time a little bit unique with that little curl at the end, separated from the regular plus sign. I know they look alike. In the case of second order, the units of K, the units of the rate constant, is 1 over molarity second. And the half-life is 1 over K A naught. We will not be going over the derivation of the half-life for the second order. We've done it for both the 0th and first order so far. I encourage you on your own time to practice or try it yourself to see if you'll get to this equation, but we will not be going over the derivation ourselves. That would be a really good extra credit question. Next up is third order. To be used to it at this point, we know, of course, that the x-axis is time. The y-axis is 1 over a squared. Its graph is also a positive slope overall, such that its integrated rate law is 1 over AT squared is equal to KT added to 1 over A naught squared. Where the units of K are 1 over molarity squared second. And the half-life is simply 3 over 2K A naught squared. Let's take it all in together and do a sample question. I'm going to draw another reaction, another table. Let's do the reaction first, and then I'll draw the table. Where is it? Right here. Okay. The reaction between 2NO, 2H2, gives us N2 plus 2H2O. And I'm going to draw a table with 4 columns and 5 rows. I'll write that out so you can see. 4 columns, 5 rows. Yeah, what's up? Yes, but in this case, we want them all to be gases, so just assume that it's at a boiling point temperature. Yep. And we have rates. Okay. Going to give you a couple of trials. Trial 1, 0.006, 0.001, 1.8 times 10 to the negative 4. Trial 2, 0.006, 0.002, 3.6 times 10 to the negative 4. For trial 3, 0.001, 0.006, 0.3 times 10 to the negative 4. And finally, trial 4, 0.002, 0.006, 1.2 times 10 to the negative 4. First question. Provide a complete rate law expression. We know, of course, that the generic form of the rate law expression is rate is equal to K multiplied by the reactance, each raised to some number, here represented as X and Y. So the first thing we have to do, the first question is really asking us, hey, calculate these values. To calculate the orders of the reaction, we're going to look at our actual experimental data. We're going to pick 2 trials. We're going to compare the rates, and that will tell us the order. As you may recall from Tuesday's class, we talked about how, although there isn't an explicit procedure to be followed, you can write down the math. You can also visually try to follow along. So let's try for the H2, let's try to do it visually together. And then for the NO, I'll go ahead and write it out. So we want to investigate what the order of the reaction is with respect to H2. We need to pick 2 trials where H2 changes, but NO does not. As you take a quick scan through these trials, trials 1 and 2 should jump out at you. We can see that H2 does in fact change, and the NO stays constant. The reason why we pick these 2 trials is any change in rate has to be because of the change in H2. We can see that the change in H2 is specifically 2 times. Even though there is a decimal place here, hopefully we can see that this is just 0.01 times 2. And if we look at the rates, the 10 to the 4 is the same, so that can be ignored. We're comparing 1.8 to 3.6. That's also 2 times. So when the concentration of H2 doubles, the rate also doubles. Is this 0, first, or second order? First order, this is a 1-to-1 ratio. When the concentration doubles, so does the rate. I don't even need to write my work down. I can just immediately write that the reaction is first order with respect to H2. That was visually. We tracked the data visually. That's an appropriate method to use. Let's do one where we actually wrote it out. Let's now try for the NO. We're going to look for 2 trials where NO changes, but not the H2. Hopefully the ones that jump out to you are trial 3 and trial 4. We can clearly see that in the case of trial 3 and trial 4, H2 does not change. So any change in rate has to be because of the NO. Maybe some of you, as you're looking at it, you're probably already able to predict the order in your head. Don't say it out loud. For NO, we're going to pick trial 3 and trial 4. And we're going to compare the two. We like to put the bigger number on top. So we're going to put the trial 4 on top. 0.002 divided by 0.001. That leads to a rate of 1.3 times 10 to the negative 4 divided by 0.3 times 10 to the negative 4. All I've done is I've just collected the data from the table. On the left-hand side, this is one's pretty straightforward. We just saw it a while ago. This is just 2. On the right-hand side, it does have an exponent. It does have a 0.3. Let's be confident. Let's put it into our calculator. 1.2 times 10 raised to the negative 4 divided by 0.3 times 10 raised to the negative 4. This is a flat 4. After this, we try to reduce this to some 2 to the n. Based on these powers, this is what tells us this is a second order reaction with respect to the NO. If you were to try to describe this to someone else in conversation, what would you say? Well, you would literally say, when the NO doubles, the rate quadruples. This is a 1-to-2 ratio. This is a second order reaction with respect to NO. We're not done yet, of course, although we have calculated the X and Y values. We can plug them in. For NO, it's squared. For H2, it's to the 1, so we can just write it as is. Now all that's left is that we need to calculate the rate constant K. We can say that the rate constant K is equal to rates divided by the concentration of NO squared multiplied by the concentration of H2. How did I get there? All I did was I divided both sides by NO and H2. Why did I drop the 1? Because anything raised to the 1 is itself, so I don't necessarily need to write it. And where will I get data or information about the rate and concentrations? We have 4 trials to pick from. And remember, it doesn't matter which trial you pick. The rate constant is the same for the reaction. So how about we just pick trial 1? Let's say use trial 1. The rate of trial 1 is 1.8 times 10 to the negative 4. The concentrations, 0.006 squared times 0.001. We put this into our calculator, 1.8 times 10 raised to the negative 4 all over 0.006 squared times 0.001. Looks like our final answer is 5,000. Now, how do we determine the units of K? Because technically speaking, it's not just one reactant, it's 2 of them. And each of them affect the rate. One of them is a second order, one of them is a first order. In fact, you can say that the overall order is equal to 2 plus 1, just 3. And according to our graph, the units of a third order K is 1 over m squared s. One over m squared s. How did we get that value? We said that the overall order is the sum of the individual orders. So the equation is overall third order. So we use the units for third order reaction. This is, of course, what leads us to our final answer, which is rate is equal to 5,000 times NO squared times H2. I see a hand. Ryla, what's up? So that would be a total of fourth order overall. We will not be seeing that in Chem 300. You will stop at third order. If I were to, for example, give you a fourth order, then it would be on me to, tell you what that unit is, just dependent on the context of the question. But I am not going to give you anything that goes beyond third order. Any other questions on this? This is just part A. Okay. Let's do a question from part B. Let's do part B, a second question. Using the data from trial 2, calculate the half-life of each reactant. All right, let me just get the data table at the ready. And of course, in case we need the rate law expression, I'll also just grab that. And all I'm doing, of course, is just putting them together so we can quickly refer to it. Okay, so the question outright says using the data from trial 2. So of course, we know what numbers we're working with. It then says to calculate the half-life of each reactant. Okay, so this is going to be two separate calculations. Drop a line kind of dividing them. This is going to be its own calculation for NO and another calculation for H2. The question is outright telling us to calculate the half-life. So we need to know which half-life equation to use. We know from the rate law expression, which we spend time on determining, that NO is second order and H2 is first order. So we just use the half-life equation appropriate to each reactant. So skim back a couple pages. Now we're looking for the half-life of a second order equation. We're just going to copy this over. For the half-life of a first order, again, just scroll back in your notes for it. Grab that equation. So now we know which equations to use for which reactant. How do we know which equations? because we calculated the reaction order. So let this be an immediate lesson. Take your time determining the rate law, because recognize if you make a mistake in part A, for example, if you happen to calculate this one over here as 2, technically speaking, every subsequent answer might also be wrong. All right, now we're going to plug stuff in. 1 over K, which we calculated as 5,000. Multiplied by the concentration of our reactant. Okay, well, how do we know which reactant? Well, we're talking about NO. So that's which reactant to use. How do we know what concentration to use? Well, the question told us using specifically the data from trial 2. 0.006. Did I miss any zeros? Nope. Put this into our calculator. One divided by 5,000 times 0.006. Pretty small looking number. That's all right. That looks like 0.033. And the threes keep repeating, so we'll just write the first two. Of course, the units. We know that the rate constant is 1 over m squared s. And that will be multiplied by the molarity. Remember, the molarity comes from the concentration. These cancel each other out, and all we're left with is 1 over ms. We can apply the same logic to calculating the half-life of H2. This will be equal to a constant 0.693 divided by the rate constant, which is 5,000. Recognize in this case, you don't need concentrations. Why? The equation doesn't ask for it. 0.693 divided by 5,000. 1.386 times 10 to the negative 4. The units are, of course, it's a flip. This becomes molarity squared per second. That's part B. That's calculating the half-life of a reactant, of each reactant. Remember that the equations will be given to you as part of the reference sheets. You just need to know how to use and exploit them. Yeah, what's up? So on top is just a number. So we're just looking at the units of K. This was first order. Oh, whoops, I used the wrong one. Thank you for catching that. 1 over second. And then that just turns into just a flat second. Yeah. Right. Part C. Using trial 3, calculate the time required for NO to decrease to 0.003 molarity. So specifically looking at trial 3, we're being asked to calculate the time required for a reactant to decrease we will, of course, be using the integrated rate law. For NO, which, of course, we've already established to be second order. Going back to a second order, what does a second order equation look like? Well, it's right here. Give this page a second. Remember, all we're really doing is applying that graphical analysis to it. We're trying to say, well, if we know what the concentration is at this point, can we calculate what the concentration or the time taken to get to that other point? Well, we just use the equation of the line. Copy that over. That way we have the equation. All right, so we have our equation at the ready. Let's be sure we know what we're plugging in. Well, we know from the previous page, the rate constant is 5,000. We know we're actually being asked to find time. So that's what we're ultimately going to find. That's T equals a question mark. We just need to be sure what is our AT and our A naught. Now, this is where those labels come really handy. Don't forget that A naught is initial. It's the concentration at the beginning. And AT is a concentration after some time has passed. Thinking about the wording of the question, it says, calculate the time required for it to decrease to. So that is what tells us this is actually going to be our final concentration. Once you're able to make that logic, the final concentration is 0.003. The initial, of course, where does that come from? Well, the question does outright tell you using trial 3. So trial 3 NO. Did I miss a 0? I think I missed a 0. Because the starting one should be, yes, there should be another 0 here. I apologize for that. There should be 3 zeros in that number. Okay. So trial 3, its initial concentration is 0.001. Now that we have all our data, let's plug stuff in. One over AT, which is 0.0003, is equal to 5,000 T. Remember K, that K value is 5,000. We're trying to find T. Add it to 1 over 0.001. With a little bit of rearranging, we get negative 5,000 T is equal to 1 divided by 0.001 minus 1 over 0.0003. Take a second to understand how I got here. I've carried over the 5,000 on the other side. That's where the negative comes from. I've carried over the fraction to the other side. That's where the negative comes from. Putting the fraction in our calculator, 1 over 0.001 minus another fraction, 0.0003. Awesome. We get right here that this is approximately equal to negative 2,333, and those threes keep going. The fact that both of the sides are negative, well, that's kind of satisfying because if they're both negative, we can actually just cancel them out. Ryla? Well, if we did it from up here, if I tried to do it immediately, then I would move that over and then divide both sides by 5,000. But the purpose of the teaching example is to show you that don't let the negative freak you out, because if you're doing everything right, it should work out to be positive. I mean, you can never have a negative time. So it was just for the purposes of the demonstration, I chose the more difficult approach. Negatives cancel each other out. To get t alone, we divide by 5,000. Put this into our calculator, that value. Let's first get rid of the negative. That's easy. Divide it by 5,000. Looks like this is 0.47. Of course, the question is being asked about time. So what unit of time are we working with? We know, of course, from the table, we're working with seconds. 0.47 seconds. Of course, time will only ever be in seconds, minutes, hours, or days. That will be evident based on the units in the table. How are we doing? Any questions? Yes. Yes, I had accidentally only written, let me just write it a little better up here. 0003. Let's write it a little better up here. Yeah. I had made a mistake when I wrote it the first time. I'd just written 2 zeros. There was meant to be a third. We have a workshop tomorrow on this topic. I'll, of course, come with everything printed. I'll give you an example of what your reference sheet is going to look like too. Do we have any questions? It's a lot to take in. This is a very brand new topic in how we're dealing with the approach. It's very math heavy. Natural logs, integrated rate laws, blah, blah, blah. It's a lot to take in all at once. I recommend revising and studying today's material in preparation for tomorrow. We're going to end lecture for today. If you have any questions, come talk to me now. If not, I'll see you guys tomorrow. Have a good day. Thank you very much.
Great, thank you. Have a great rest of your evening, afternoon.